Okay, so given a function, absolute max and mins on an interval. So how do you find absolute max and mins? You do what with that function? First you find, yep, you need the derivative and then set the derivative equal to? Okay. Remember? See, I don't write everything down, so it's good it's getting recorded. When you find those x values are not the max and mins, right? It's where they're at. What are the actual max and mins? The y values. Okay, but your max and min are the y values. And the other piece, if you're on this closed interval from A to B, what do you also have to check? The endpoints. You got to check those endpoints. Meaning you need what f of A is, and you need what f of B is, and they may be, if their y value is the highest, then that's the absolute max. All right? So do make sure if I give you a basic function, you can find the derivative, set it equal to 0, use your endpoints, find all your max and mins. Okay? So that was one of the things, just working with max and mins alone. Second thing, we went into those those theorems. The first one was Rolle's. Okay. How do you verify Rolle's theorem? Well, if you're on an interval, okay, what's the first thing you have to check? If you're actually given that interval, what do you got to check? You got to make sure, yeah, it's got to state that it's continuous. So if it's a polynomial, you automatically know it's continuous, right? If your f of x is a polynomial, yes, it's continuous. And then what else do you have to check on that interval for Rolle's? Yeah, you have to make sure that f of A actually equals f of B. That is if you are given the interval. Now, we've also done it where you weren't given the interval, in which case you just found where it crossed the x-axis because they would both equal 0. Remember? If you're not given an interval, then just find your x-intercepts. Find your x-intercepts. Because if you find your x-intercepts, you know, and you got 2 of them, then f of A equals f of B because they're both come to 0. All right? That was one of the other things we kind of talked about. Find your x-intercepts. Once you have determined that you can do Rolle's theorem, you then, the last piece, let's suppose we're back on the interval, or even if the interval, whatever this interval is you found, with your x-intercepts, how do you check it then? You still take the derivative, then take f prime of x, set equal to 0, and where should that x value be? Remember we checked? Because for Rolle's theorem, let me do this. Remember for Rolle's theorem? Right? If here's your 2 points, A and B, so yeah, you can see f of A equals f of B, right? Rolle's theorem states there must be some value x, yep, that has where f prime of x equals 0. So all you're checking is that that x value is between A and B. That's it. You've done those 2 things, you verified Rolle's. You do the first step. If the first step doesn't work, you're done. You don't have to do the second step. You do the first step, meaning you found f of A equals f of B. Then make sure there's an x value where the derivative equals 0, and that x value is between a and b. Okay? All right. That's rows. Now I'm going to move up. Huh? I can see you guys. I have to work on the handwriting. Definitely have to work on my handwriting.
It's cleaner than mine, believe it or not. When I started writing,
but it's nice being able to see your faces while I'm teaching and not turning my back to you. All right. Third one. What do we do after Rolle's theorem, everybody? MVT. The mean. Okay. We did the mean value theorem. Mean value theorem was a little bit different. Remember, we said it was kind of like, I'll draw the picture. Mean value theorem was slanted rolls, right? It's a slanted roll. All right. And then we tried to find this value C. So we still have our endpoints A and B, right? Yes. Yes, because, and the whole idea of this one is since there's an f of A that equals f of B, okay, that had to loop back around at some point. In order for it to do that, there had to be a max or a min in there. As the slope. Yes. So for mean value theorem, because we're on this slant, we can no longer say the derivative equals 0, right? We have to figure out what that slope actually is. So you've got to find the slope of the secant line first. So the first step is find m of the secant line. So m of the secant line is going to be, of course, f of b minus f of a, right? It's just slope, change in y over change in x. F of b minus f of a over b minus a. That is just your slope formula, right? Using a's and b's and f of a's and f of b's. So once you get that value, we'll call that slope of that secant line. Once you get that value, now what do you do with your derivative? Yes, you need to find the place where f prime of x equals the slope of that secant line you just found. Does that make sense? You're not setting your derivative equal to 0. You're setting your derivative equal to that new slope you found. Okay? Once you figure out that x value, where should that x value fall? Yeah, x should be somewhere between A and B. That's all you're looking for. You're just verifying that. Okay? So do make sure you go over mean value theorem. And I think that one was on your last lab, which is all graded. I did grade those, right? Please tell me I graded them. Yes. I'm a little behind in grading, but it's not your guys' grading. It's my other class's grading, apparently. Well, I see you. They're all online, so I don't see them, so I kind of forget that, oh, wait, they just took a test. I got to go grade that. Oh, gosh. I have one of those middle children, and she believes that. It is a real thing. How many any middle children in here? It is. Hope you guys don't feel that way. And my daughter should in no way feel that way, but she does. Do they? That's just life. It's just life. Okay, then we moved on to graphing. And with this graphing piece, so just to recap, I'll put this up here. So this was 4.1. Okay. Mean value theorem, I believe, was 4.2. I have my book so I can put the right sections for you. Graphing covered a couple sections. That was 4.3 and 4.4. Yeah, mean value theorem was also 4.2. 4.3 and 4.4. Yeah, it was kind of, we combined them. 4.3 is called what does the derivative tell us? And then 4.4 is graphing. So that we put them together. So this is 4.3 to 4.4. And it was graphing. Oh, you're given the function. You just take the derivative of the function. No, there's two things you're doing. So you're given a function f of x. So you can find the derivative of that function. You have to set it equal to this slope. Okay? Because the slope is the secant line. Okay, so what's going to happen is you're going to find then, if you set this, because remember, derivatives can be anywhere along here. We want the specific one that has this slope. So when you solve for it, you're going to end up with that x value. And you're verifying it, meaning you're showing me it is between your A and B you're given. Okay? Graphing was tricky. Graphing, there were multiple pieces to it. So I'll kind of tell you what will be on the test. You do have to understand these two pieces. The first derivative test. The first derivative test lets you know, this is where, we're not going to do an example. It's all, this was the big lab. You did like 3 of these real big. The first derivative test, remember you find your derivative, set it equal to 0, and build the intervals. And that tells you where is your function. It lets you know where f of x is increasing and decreasing. And it kind of, also let us know where there were mins and maxes, right? Because if your function increases and then all of a sudden starts to decrease, you know you have a maximum. Okay, so there are a lot of things you can find out there. And what did your second derivative test tell you? Yep. Concave up, concave down. And this is where we put all this together in that chart, and it really gave us a clear picture of what our graph would end up looking like. Couple things that are important that you'll have to do here. You might just be given a function and said, hey, find where this function, for example, I'll put some simple examples down. What might you be given on a test? Suppose you have a basic f of x. Okay? You might be given a function and asked, hey, find where it's increasing and decreasing. It just takes me a long time to write. That's why I don't like this. But I don't like writing on the board either because it takes me a long time to write. All right. So I'm going to work on that. I'm going to work on that handwriting. That looks pretty bad. So find where f of x is increasing, decreasing. And yes, that is first derivative test. Okay, you got to know that. So if I ask you find where it's increasing and decreasing, you got to think, oh, let me take this function. Let me do the first derivative. Find the roots, and then look at all those intervals. Where's it going up? Where's it going down? That kind of thing. If I ask for concavity, you have to know. Do the second derivative test. So let me throw this out another way, because these whole 2 sections were about understanding the relationship between the graph of the function versus the graph of the derivative or the graph of the second derivative even. So here's another example. let's suppose I gave you the graph of the derivative. I don't give you the function at all, meaning I don't give it to you in equation terms. I just give you the graph of the function. And let's make it up. Let's suppose it looks like this. Okay. All right, so let's pretend that's the graph. If I give you the graph of a derivative, can you tell me where the original function is increasing and decreasing? I hope so. So this is understanding, wait a minute, that's not the graph of the function. That's the graph of the derivative of the function. Without knowing what the function is, where is f of x increasing? So that's what I mean by you got to know these relationships, right? So when you look at that graph and I ask, hey, where is f of x increasing? It's increasing where the derivative is positive. Okay, I don't want you to get confused and go, oh, well, it's increasing to here. So let's throw some numbers in because we really can't do this without any numbers in there. Let's make that a 1. Let's make that 2. Let's make that 2.5, 3, whatever. Okay, so where is your graph increasing? We need this one. Let's make that negative 0.5. Yes, your graph is increasing between negative 0.5 to, not negative point, yeah, negative 0.5 to what, everybody? 2. I want everyone to get that. Where is my function is, my derivative is positive between negative 0.5 and 2. Where else is it positive? Right, but I'm asking you, where is the graph of the function increasing? It's increasing where the derivative is positive. So where else is it increasing? All right, that's what I mean by knowing the relationships. Where is it decreasing? So it's decreasing from negative infinity because the graph is below the x-axis. From negative infinity to negative 0.5 and between 2 and 3, correct? Okay, notice I'm not including these endpoints because what's happening there? At those points, it's neither increasing or decreasing. It has a derivative of 0. So the next question would be, all right, could you tell me where there is a possible minimum? Where does the original graph f of x? So, all right, for something to be a minimum value, your graph has to be decreasing and then do what? Yes, that's how I want you to think about it. For there to be a minimum value in your original function, the derivative has to go from decreasing to increasing. So where does it go from decreasing to increasing? At negative 0.5, right? So there's a possible minimum value at, you don't know what that minimum value is. You just know it's possibly at negative 0.5. Is there another place where the graph goes from negative to positive? Yeah, once you get the idea, isn't it 3? 3. And the graph itself has to go from negative and then from to positive, the derivative graph. So where else does the derivative graph go from a negative value to a positive value? At 3. Okay? Yeah, you're finding where they're at. So, yeah. And you can do the maxes as well. You're just going to do the opposite, right? Possible max values at. So again, think about a maximum. Now my graph has to be, my derivative, my f prime of x is positive and then switches to negative. So where is my graph? Positive, and then it switches to negative at 2. And that's it. That's it. So again, take time to understand relationships. I can give you the function and ask about concavity, in which case you've got to quickly find the second derivative. I can give you the function and ask about where the original function is increasing, decreasing. You only have to find the first derivative. I can give you a picture of the derivative and ask you questions about the function. That's all understanding the relationship, which you will get out of if you just read through the notes again. We did a lot of this, and then there's a lot of pictures in the PowerPoints. Read through the notes for 4.3 and 4.5. The other thing, which I will have you do one time, you had to do 3 times in the lab, right? Yeah. Fully graph a function. Now, what does that mean? I'm going to give you the checklist of everything you have to find. I am not going to give you something that's going to take you forever. In other words, if I give you a rational, I'm not going to sit and make you find those derivatives because then you got to use quotient rule and it takes a long time. I'll give you the derivative functions. I'll give you f prime of x. I'll give you f double prime of x. If I give you a polynomial, though, you can find those derivatives on your own pretty quickly, right? Yes, you can. If you can't, sorry. No, you don't. So yes, go back to, this is actually in 4.4. They have the graphing checklist. You don't need to memorize the checklist because I'm going to give you a sheet that'll ask you questions along the way. Where is the mins? Where are the maxes? What is the first derivative? What is the second derivative? What are the roots? Remember, these are all the things we talked about. Where is a possible point of inflection? This is where you do that little table of charts. So just look through our notes on 4.4. Look through your lab from the first half of chapter 4. We have lots of examples of this, of doing this, okay? But yes, you all have to fully graph one function. I will not make it a trig function, okay? Or an ln function, okay? It'll be a polynomial or a rational. And if it's a rational, I'll give you the derivatives. If it's a polynomial, you're finding the derivatives. Got it? So please look over that lab. What lab number was that? What lab number are we on now? 9. 8, 9. So was lab 7? Well, 8 and 9 were together. So it was called lab 7, I think. Damien. Oh, there could be other places, yeah. Huh? No. No, you don't, because you're supposed to know that. Do you remember on my in my Canvas course, it says everything you need to know before starting this course, and guess what was in there? You don't need to memorize it. You just kind of go through it and figure it out. I'm not going to give you anything that's going to take you tons of time. You really only need to know this, right? You need to know pi over 4. And you need to know this one.
See, but your calculator does it. So if you memorize a decimal, then you'll.
We just use reference angles. Oh my God. We're not getting into a trig conversation right now. All right, let's move on. You have to do one graphing problem. So look over those ones from the lab. I graded, everybody has access to those labs because you were in those groups, so you can look at my comments and look over one of those.
Is there still going to be like 5 true false?
I'm not, I took the true false, I didn't put any true false because we need more time for everything else on this one. So I will say that. No, notice I didn't start with that. No true false on this one. I know some of you like them and some of you do not. No, the extra credit, you already know what that is. I'll put it up here again. All right, 4.5, optimization. You will have two. They will look like any of the ones we did in class or ones you have on your lab. That's what I can guarantee you. Okay? I'm not going to give you anything that's not very similar to something we did in class or something you did on your lab for the optimization problems, okay? And we just did those. I'm just telling you they're on there. We did 3 in class. Well, we did a quickie. All right, they're not going to be as simple as expanding a square or a circle. All right, that was just to kind of show you what to do. But the other ones we did in class was the barn problem. Look over that one. You should have that one in your notes. It's on the notes on the PowerPoint. We did the box to fit under the seat for the airline. Yeah. Yes, we did. Everybody's frowning at me. Well, it was supposed to be the airline regulations. Maximize the box. The suitcase. Yeah, the box, the suitcase, We also did cleaning the tank. We did the cylinder. Cylinder problem. That was the cylindrical tank. On the lab, 4.5. We just did in class. 4.5. No, you're thinking of related rates. It's a little different. This was 4.5. You also had the one which you have on this lab where you have a box on the x-axis, that's a rectangle on the x-axis that's inside a parabola. The parabola provides the constraint because you have to optimize the area, but the parabola provides you a way to write the y value basically. Yes, you only find the constraint function is to get rid of one of the variables in the objective function. Because remember, you got your objective function. This is what you are setting. Get derivative. And set equal to 0. But you also have a constraint function. And you use the constraint function so that you only have one type of variable in your objective. So the constraint function is just used to replace a variable in your objective. So a lot of you were working on the rectangle inside the parabola. The rectangle is an area, x times y, or you would have used 2x because you had x on either side. You would have used 2x times y. That's your objective function. But you can't have an objective function that has two different variables in it, an x and a y. So you use the constraint of the parabola to replace y with 48 minus x squared. Then you go and find the derivative because you only have one variable. So do look over those two, very similar to two that are either on the lab or the ones we did in class. Okay? Then L'Hopital. This was 4.67. Okay, we'll go back to 4.6 when we go through the extra credit. So 4.7 was L'Hopital. You will be given, I don't know how many, let's say 2 to 4, okay? I have to still make up this test. I got to figure out. So let's say you'll be given 2 to 4 limits. And this test, you must use L'Hopitals on them. Actually, it's the only thing you can use. When you take the final, you're just going to be given a bunch of limits and you use whatever you want. Now, indeterminate form. Don't forget. In order to use L'Hopitals, that's me trying to abbreviate too much. You need to first show me that your function comes out to this. In other words, you first try to find the limit as it is. And you go, and you show me, oh, indeterminate form, then you apply L'Hopital. Okay? So you got to show that indeterminate form first. Yes?
If, with the infinities, if the top is negative and the bottom is positive,
Doesn't matter. Then apply L'Hopitals. Okay, so you show me, oh, if I have, tan of 3x, I think this one's on your lab, over tan of 5x. When you plug in 0 for tan of 0 is 0, right? Isn't tan of 0, 0, everybody? So you get 0 over 0.
Just a quick question. So if we have something like sine over sine or tangent over tangent, but we have like the same variable x and they're both to the same power and they both have coefficients, wouldn't it just be the coefficients over each other? So like if we had 10 of 3x over 10 to the 5x, we just want to check our word. Is that like a thing that
Right, but you still got to go through and show the work on L'Hopitals.
Is that like a thing that
Yeah, if you have, because you saw that in the lab, I forget what the actual numbers were. I'm saying tan of 3x over tan of sine x, because what happens is you go and find the derivatives, which ends up being secant squared of 3x, but the 3's out front because of the chain rule. Tangent secant squared of 5x with the 5 out front. Because secant and tangent, or the secant of those values are 1, yes, you end up with, same with sine. If you have sine of 5x over sine of 6x, it does end up being 5, 6. Because when you take the derivative and use chain rule, it's 3 times 1, because now you're doing cosine, which is 1. It applies with those two. Yep. So don't forget that. Now, there were other versions. We also did this was the other one. So I'm going to take a big red X. I'm not going to give you that one. We didn't even do that one as an example. It was in the notes for you to look at. You might have to do it in Math Lab, but I'm not going to give it to you on the test. Would you? Huh? I can. I can only put so much. But if I do give you this one, okay, as it stands, that is not L'Hopitals, but you can do what? Apply a little algebra magic, remember? And you need to get it. Yeah, get it to 0 over 0 or And you did that, remember, by taking whatever, it's usually the simplest one. Now, I will say on the lab today, there's one that does this where it's the one you don't think you should do that you should do. I don't know if that makes sense. But you have to make it 1 over x, basically. I think we did an example of limit. What did we do? X goes to 0. X ln x, right? Technically, this is 0 times infinity. It's times negative infinity, but that doesn't matter. It's 0 times an n infinity, right? Because ln of x, as x goes to 0, actually goes down to negative infinity. So 0 times infinity. So I said, okay, because this, oh no, I got rid of I lost my thingy. I lost my pens. Hold on. This is what happens when I was doing so well. This little thing is in my way. I don't know how to move it. Oh, there it is. Got my pens back. Happy. Okay. So this ends up being 0 times negative infinity. So it's not a L'Hopital's rule, but we can rearrange it. And what was the quickest way to rearrange that one? I'll move it up. Do you remember? You keep the ln x, and where do you move? When the x moves to the denominator, what does it become? Yeah, then it ends up being 0 negative infinity over infinity, right? Yeah. Yeah, so that's now, and again, the negative doesn't matter. It's n infinity over n infinity. At that point, you're good. Now you can go ahead and apply L'Hopital's rule. Okay? The fourth piece to that was a function to a function. The fourth piece was when you have the limit of a function raised to another function. This was a 2-step process. Remember, we use this idea that e to the ln of x just equals what, everybody? Huh? You remember that? E to the ln of x just equals x. So we kind of use that idea. And we say, all right, well, I'm going to raise f of x, g of x. Technically, I'm going to raise it to the e of f of x. Sorry, I forgot my ln. Let me redo that. E to the ln of g of x. Remember that? And then I use the power rule for natural logs to move the g of x out front. Okay, so 2-step. All you got to remember is the 2-step process. First step, we're going to define a new limit. We're going to call it L. And that is just going to be the limit of f of g of x times ln f of x. Yeah, it's the limit as x goes to whatever x is going to, I'll call it a, of g of x times ln f of x. Okay? This is a great problem because it uses everything. What usually happens here is you end up with 0 times infinity. So you end up with something like this, which means you then have to get it into this form, and then you have to use L'Hopital's rule. Okay? So you can use L'Hopital's on that. Use L'Hopital's to get that limit. And then the last part is you have to undo what you did by raising it to the e. To L. Yeah. And then take e to the L. So that's going to be, because in the end, the limit of f of x to the g of x is going to equal e to whatever L ends up being. Okay, these are the problems we just did, and you do have one of them on the lab. Since we just did this, do you want to do like, we did a couple examples. Did we do the, yeah, we did that example. Should we try another one? You want to do one example of these? Okay. Let me find one. Limit of f of x to the g of x. Oh, this one is an ln right here. That's natural log. Yeah. Yep. Yeah, x to a. Yep. All right, so here's an example. It's just a common one. Let's find the limit as x goes to 0 of, I found it and then I lost it. Need space. You have to truly understand what does this mean? This means what? E. Okay. Does that make sense? E to the y equals x. That's what that means. Everyone agree with that? Okay. So, if I took e to the ln of x, right? I'm proving to you that this just equals x. You take e to the ln of x. What does ln of x equal? Well, that's the same as e to the y. But what does e to y equal, everybody? X. So it just all comes from this idea. So I'm going backwards. If I have this, well, that's going to be the same as e of f. They're exactly the same. So I'm replacing it. I'm replacing it with the same exact value. Yeah, and that equals e, because I can move it out front.
Because over there you don't have an e in the first part, and then it just went up.
Because I said that equals that. Okay, you got to digest that one, especially if you're moving on in calculus. You got to really understand those relationships. All right, let's do one quick example though, so we can go through the steps and you have it. So the first step is let's set L. And this part you may just need to memorize. Set L equal to, the 2x goes out front, 2x ln of x. All right? That's your first step. Now, if I plug in 0, as x approaches 0, 2 to the x is going to go to 0. That's going to equal 0 times, as x approaches 0, and this is only from the right, don't worry, that plus will be there. The reason that plus is there is because we can't approach 0 on ln from the other side. But as it approaches, where's it? It's not going to ever hit 0, but where's it headed? Down to infinity, right? So it's times infinity. Negative, but that's okay. So that tells us, okay, now I just need to Yep, take the limit as x goes to 0. Keep the ln x and move the 2x down here. Because now I get an indeterminate form that we can use L'Hopital's rule on. Because what is that now, everybody? Yeah, which is indeterminate. But it's indeterminate in such a way that I can now, okay, that's what I write in my notes to let myself know I'm applying L'Hopital's rule here. I'm applying L'Hopital's rule. L'Hopital's rule says I can take the limit. All right, what is the derivative of ln x? Okay, because applying L'Hopital's rule, that's what tells me you're going to now take the derivative of each piece. Numerator separate from denominator. What's the derivative of 1 over 2x? If you don't know, find real quick off to the side. What is that? You could do, it's 1/2 x to the negative 1 if you need to, right? If you don't have that down yet in your head, change the 1 over x part to x to the negative 1, right? So then it becomes negative x to the negative 2, which is negative 1 over 2x squared. Okay? Well, now you just got to do the algebra. And this is where you fail. No, what's 1 over x divided by... Oh, that's 1. Oh, if you need, go back to like 3rd grade and actually write out the fractions. Seriously, right? 1 over x divided by negative 1 over 2x squared is 1 over x times negative 2x squared, which equals what? So it becomes the limit as x goes to 0 of negative 2x. All that work, and what does it just equal? 0. That's it. All that work, and it just equals 0. So basically, my writing is exactly the same whether I write on here or on the board. So it doesn't matter, right? Okay, good. All right. Take a picture of the rest of it. Anything on there is in the notes. I can post the note and I'll post the video, and if anybody really wants to look at it again, you can.
Thank you.
And then I'll try next Thursday teaching using this, and we'll see how it goes. You guys are my guinea pigs because you've been such a great class this year. Last piece. Oh my God, what number are we on? I told you, it's a big test, isn't it? It's a big test. That's why I pushed it. I didn't want to give it today and only give you Tuesday to Thursday. I want to give you the weekend to study. So sorry for ruining your weekend. And what did I say? Oh, I switched from numbering it to actually thing. 4.7. Not 8. 4.9, the antiderivative. Okay, that's just going backwards. We just did that. We just did this last class. So there's 2 things. Couple things to remember. Okay. That integral notation, you're going to know exactly what that means when we do Riemann sums, by the way. That integral notation. So let's suppose we are doing what we call indefinite integrals, and we'll get into that, what we mean by indefinite versus definite, next chapter. So let's suppose it was 3x squared minus 5x plus 2. And we'll get into why we put the dx there. Now, right now, you're just going to accept it. So, how do we do an antiderivative? We work our way backwards. What's the 3x squared? So remember, normally, We multiply and go down by an exponent, right? We have to go do the entire opposite, which means we do the exponent part first, but instead of going down, we do what? We go up and divide by the new exponent. Then we do the same thing. We go up and divide by the new exponent. And even if there's no x on there, because technically there is an x attached to that 2, and what is the exponent of that x that is attached to that 2? 0. It's there. We don't ever write it, but it is there. So that 0 goes up to 1. Oh, divide by 1 doesn't do anything. Now, remember, we lose something when we take a first derivative. So we got to put it back in. We just don't know what it is we lost. What do we lose? We lose the constant. So just add your c. And then you're done. We can find the constant. Yes. So go up 1, divide by that number, the new exponent. See? 1, go up to 2, divide by the new exponent. You can clean it up. Okay, at this point in your life, do not leave a 3 over a 3. Okay? I'm sorry. What? we can eliminate the 3s, right? We can do that much. You can, if I give you more information, you can figure out what that constant is. I'm going to make it simple. So I said, oh, find it when, what if I went f of 0 equaled 1? What if I add that piece? How does that let me narrow down my constant? Yeah, I plug in 0, right? Which gives me what? 0. All right, I picked 0 because I feel like doing a lot of math right now. 0. And it equals 1. So what does c equal? Now, when you do that, don't forget to go back and give me the original function. Okay? Sometimes we call that capital F of x. Okay? If you are not given a point on that function, this is what essentially this is, a point on the function. If you're not given a point, you can't find c. If you are given just 1 point on the original function, you can find your c. Also, don't forget, you are expected to not only do these polynomials, you are expected to do your basic trigs and your ln's and e of x. So in other words, you're also expected to find the integral of, say, sine x. Yeah. All right, so you have to go backwards. Let me finish this one problem. How do I know? Stop yourself and say, okay, everybody, what's the derivative of negative cosine? Well, derivative of cosine is what? Negative sine. Negative times negative sine is? Check yourself. You can always check yourself when you're doing an antiderivative by getting your answer and taking the derivative. Okay? Don't forget that. You can do that. I can also put in here, hey, find it when, I don't know. I'll make it easy and then I will get to your question, I promise. Let's say f. No. No. F of pi equals 2. You, it's almost Thanksgiving. You can have pie then. Pumpkin pie. You can all have some pumpkin pie at Thanksgiving. So what do? You just plug in. Okay, what's cosine of pi? -1 times the negative sign, right? Plus c equals 2. So you have, yeah, I got 1 plus c equals 2, c equals 1. So that just means when I write my original function, the answer is negative cosine x plus 1. There you go. That is your test. Yes. So at this point, if you have a coefficient, you mean like that? Okay, here's what's nice about the integrals. They work like everything else. If you have a number, where can you stick it? Out front. Right? And then what's the antiderivative of secant squared, everybody? That's it. Yeah, that's it. There's really nothing you need to worry about it. Okay, I'm going to stop recording.